Oh my gosh, you guys are already been introduced to a mole, so I'm going to tell you some kind of ways to think of how big that number is. And it's actually based on one isotopic form of carbon. So if you have 12 grams of carbon-12, then you have a mole of carbon-12 atoms. So as you guys know, a mole is equal to 6.022 times 10 to the 23rd. So I'll ask this in the form of the question. How many people think that there's uncertainty in Avogadro's number as written? Like I answered rocket. Yes, there is uncertainty in it as it's written. So how many sig figs we got? 4. Yep, very good. Yep, 4 sig figs. So 1 mole is equal to 6.022 times 10 to the 23rd of anything. Okay? So I'm not going to do it here, but you guys know what that would be. It'd be 6.022, and then what, 20 zeros after that? That's how big a mole is. The abbreviation for mole kind of tickles me. You get to drop the E. Instead of M-O-L-E, it's M-O-L. You guys probably know this, but like in Mexican food, they have this mole, I think it is, out there, and I just giggle whenever I see that in the stores. So the concept of a mole is kind of like the concept of a dozen. So you're literally counting things. So the reason we have to have such a big number to count things in chemistry is because things are very, very small. So if you have a dozen of anything, you have 12 of those things. If you have a gross of anything, you have 12 dozen or 144 of those things. If you have 1 mole of anything, then you have 6.022 times 10 raised to the 23rd power of those things. Well, a mole is usually used for atoms and molecules and formula units. But I'm going to talk you through some things that are bigger than atoms and molecules and that sort of thing. So rice, right? Uncooked rice. You know how like in the, like they have a jar of jelly beans, you're supposed to count the jar of jelly beans, okay? So what do you think? How many pieces of rice are there? What do you think? How many people think it's more than 100? Oh. How many people think it's more than 1,000? I'm not quite sure. I know I wouldn't be sure either. I had the answer to one. How many people think it's more? You counted that? I waited and then, wow. Yeah. I didn't count them all. How 1,000? Okay. How many people think it's more than 5,000? Okay. It is actually 2 times 10 to the 4th. So final answer. 20,000 pieces of rice grain. You're like, are you serious? And then I actually have the conversion here. We're going to do some conversions from counted number of pieces of rice. If we convert that to moles, that actually is, with 2 sig figs, 3.3 times 10 to the negative 20th moles, which is a fraction of a mole. Okay, so that's, now this says if you were to have a mole of rice grains, that would cover the whole world, the land area of the world, which the world is what, 3/4 or so water, 2/3, I don't know, but a lot of it's water, so what land we have would be covered with rice up to 75 meters, which is not good. Again with the rice, if you had a mole of rice, that would be cool, and a lot of people eat rice, right? And if you had a mole of rice grains, that still would be more than the number of rice grains that have ever been grown since the beginning of time. So good luck gathering a mole of rice grains. If you had a mole of rice grains and you gathered them together, they'd occupy a cube that is 120 miles on each side. 120 miles, 120 miles, 120 miles. That's a lot of rice, but that's how big a mole is. Switching from rice to marshmallows, I was thinking of the Stay Puft Marshmallow. Don't think of anything, clear your mind. And then, yeah, he thinks it. Anyway, so if you had a mole of marshmallows, that would cover the United States up to a depth of 600 miles. All right, snowflakes. cover the United States up to a depth of about 2/3 of a mile. So now this is, let's see, you know, per second you go 1001, 1002, 1003, 1004. So if you're trying to go ahead and count up to 6.022 times 10 to the 23rd counts, you could go ahead and have everybody on Earth doing that, which would be interesting in itself. But at the time this was written, you would need 51,000 times the number of people that were on Earth, counting 1001, 1002, 1003. And if we were all counting, it would take 75 years to count up to a mole. I know. You're like, really? And most of these can be calculated using the factor label method we've been talking about. You kind of start with what you know, and then you end up with something, you end up with the answer to this, a mole. So computers are pretty fast. At the time this was written, a supercomputer could crunch instructions at 1,000 millions of instructions per second. So it's a fast computer. That's the point here. That same computer could go ahead and count the number of people in the United States in less than a second. So you know, if you've ever done anything with programming, you like tell it to count, like count, been in a loop. So it would do that number of iterations or number of people in the United States in a second. But that same very fast computer, if you're like, okay, dude, okay, computer, I want you to do this for 6.022 times 10 to the 23rd times, it would take it 1.9 million years to do that. And that's one that I've actually done the factor label on. I'm like, that is so interesting. Hockey pucks, okay. The mass of a mole of hockey pucks would be equal to the mass of the moon. Again, problematic. Basketballs. The volume of a mole of basketballs would fit in a ball bag the size of the Earth. And pennies. Like, how many of us, I just blow off pennies, like, right? You know. So if you had a mole of pennies, and all you have to do to think how many dollars that would be is what to move the decimal place over a couple places, and that's how many dollars you have. So if you have a mole of pennies, you have a lot of dollars. At the time this was written, you could give it to every person on Earth, and this is how many pennies they would receive at the time this was written, 1.5 times 10 to the 14th pennies. Again, how many dollars is that? 1.5 times 10 to the 12th dollars, right? And people could go ahead and spend their money by at a rate of $1 million a day, and then that person wouldn't live this long, but at that spending rate, they could spend for 4,000 years. But you wouldn't want a mole of pennies. This is like I Dream of Jeannie, where people would ask her to blink in something, and she would blink in something that was problematic. If you had a mole of pennies, this would be bad, because it would cover, again, all the land area up to the depth of about 420 meters. So, yeah. Anyway, a mole is a really big number. Here's a figure from your textbook that says, and I could have asked you how many water molecules do you think is in this one little drop? And the answer is, well, it doesn't say it, but it says the number of molecules in that water droplet is 100 billion times greater than the number of people on Earth. Just think that way. It's neat. They're really small. That's why there's so many in such a small volume. Okay, enough of the silliness. So this is an equivalency statement. 1 mole is approximately equal to 6.022 times 10 to the 23rd of what you're counting. So with any equivalency statement, we can come up with two ratios we can use as conversion factors. It looks like this and like this. So the relationship between these two are what? They're reciprocal of each other. And it's just like when we're working problems. How do you know which one you're going to use? You look at your units. So let's work a few problems. And again, well, you know you can use this as a conversion factor between what? Well, between moles and atoms. Moles and atoms. Okay? That's what we can go back and forth between. So we'll work these two problems. How many moles? Now, the way this is written, you see the brackets, the square brackets up there. In my problems, when you see square brackets like that, it's, I'm going to say optional. What I mean is it's optionally written. So usually when I do this, the stuff in brackets won't be there. Usually it will read, how many moles is 1 trillion hydrogen atoms? Okay? That's what I mean. And the second one, how many atoms is 0.555 moles? Okay. Now, the first one I say hydrogen is the element, but I wouldn't have to say what element it is in this case, because for all elements, it has this relationship. 1 mole of atoms of any element is equal to 6.022 times 23rd of those atoms. My advice in working these is usually to start with the thing that's unique to the problem. So in the first one, I'm going to start with 1 trillion hydrogen atoms over 1. The second one's going to be 0.555 moles over 1. And then I'm going to use one of those two ratios on the previous slide. For this first one, if it's okay with you, I'm going to say 1 times 10 to the 12th. 1 times 10 to the 12th. That's what 1 trillion is. And let's see if we can round this. I'm going to go ahead and I'm going to say that that's exact. It's kind of weird, but we're going to say that that's exact. So we're going to put that over 1. So we want units of atoms to cancel, so what units will go on the bottom? Units of atoms. So on the bottom, it's going to be that 6.022 times 10 to the 23rd hydrogen atoms, or atoms. Just kidding, hydrogen atoms. And then the top is going to be 1 mole hydrogen. So hydrogen atoms cancel. So this would probably be over 1. It's probably what I would do. Hydrogen atoms cancel. We're left with units of moles of hydrogen, which is perfect. All right, so I said we're going to go with 1 trillion exact. And what would we say about Avogadro's number? Is there uncertainty there? Yeah. So how many sig figs? I'm liking 4 sig figs. Yep, 4 sig figs. And if you're like me, it's fun to put numbers on a scientific notation. It's fun to put them in your calculator, I think. You put it in your calculator, round towards significant figures, you get 1.661, excuse me, 1.661 times 10 raised to the negative 12th hydrogen atoms. Excuse me. Ugh. My units are moles of hydrogen. Final answer. 1.661 times 10 to the minus 12 moles of hydrogen. Okay, for the next one, our starting number is going to be that 0.555 moles over 1. If I want moles to cancel, what units are going to go in the denominator? Moles. So now we're going to put 1 mole in the denominator, and we're going to put 6.022 times 10 to the 23rd atoms in the numerator. So moles cancel. Now, is there any uncertainty brought by 0.555? Yes, there is uncertainty. How many sig figs there? 3. Yep. Cool. And we said 4 here. Yeah, feel free to definitely grab your calculator if you want to tap some of these in. I think that's fine. Yeah. Okay. Is that what you got? 3.34 times 10 raised to the 23rd power. Now, working all science problems like this, chemistry or biology, I guess, or physics, you want to say, does that seem reasonable? Does that make sense? Well, I have less than a mole, about a half a mole, and over here I'm ending up with, instead of 6.022 times 10 to the 23rd, I've got 3.34 times 10 to the 23rd. It's reasonable. Up there, does it seem like you should have that small of a mole based upon that number of atoms? Well, you definitely don't have a whole mole if you're not up into 10 times 10 to the 23rd. You're only times 10 to the 12th. So that fraction of a mole seems reasonable too. So kind of take one more look at, does that seem right? All right. In another class, in another universe, I would say, that's enough for today, and we'll just go home. Oh. But I kind of feel, because we're switching gears here, but I know we got to keep moving on. So in science, there are sometimes words for things that make sense, and sometimes there's words for things that don't make sense. Molar mass is one of the things that makes sense. Molar mass. What is it? It is the mass of 1 mole. That's what molar mass is. Mass of 1 mole. I'm liking it. So all you got to do is get 1 mole of anything together, weigh it, and that's the molar mass. A little bit ago, what did we say? Was it that if you get a mole of hockey pucks together, then it's going to weigh the mass of the moon, right? That was it. Okay. So the molar mass for hockey pucks is equal to the mass of the moon. That's the molar mass for hockey pucks. But we're not going to go to hockey pucks. We're going to say very small things. So what is the molar mass of, or what's the mass of a mole of copper atoms? Okay, that's the sort of thing we're going to talk about. Molar mass. So units of molar mass are going to be grams per 1 mole. Grams per 1 mole. Molar mass. Written, a third way to write it would be G/MOL. So there's kind of 3 ways. This is the one that you're going to have to, when you work problems, that is how you're going to have to kind of unpack molar mass. Grams per 1 mole. Okay. All right. So I mentioned copper, and because we saw some pictures of copper the other day. So if you have a mole of copper atoms, which would be very hard to count. You wouldn't want to count these guys, so you wouldn't like to use a mass thing. I'm going to go over here and find copper. It's atomic number 29. It's got 29 protons in the nucleus of a copper atom. This decimal number the other day we said was how much a copper atom weighs. What were the units of that? AMUs, yeah. So I'm looking up here. It says 63.546 AMUs. That's how much copper atom weighs. That, by the way, is also the molar mass of that element. So to get 1 mole of copper atoms, we would weigh out 63.546 grams of copper. That would give us 1 mole of copper atoms. Okay, so to me, that decimal number serves 2 purposes. Okay, the molar mass is numerically equivalent to the average atomic weight. What is the average atomic weight? It's the decimal number on the periodic table. Okay, but you told me that we use AMUs for average atomic weight, and we use units of grams per mole for molar mass. So, right. I'm going to kind of take, is it the next slide? I'm going to kind of take you through a proof of why that is. Here's your proof. Yeah, and we'll pick on copper. To 4 sig figs, the decimal number for copper, its average atomic weight, is 63.55 AMUs per 1 atom. Do you guys remember the relationship? How many AMUs are there in 1 gram? 1 gram is equal approximately to 6.022 times 10 to the 23rd AMUs. Yep. And I've never asked students to memorize that, but I just think that's pretty cool. Sounds like a by definition thing, doesn't it? So if we do this, then what? Our AMUs cancel, and we have grams per atom. And we want grams per mole. So we need to, so our AMUs cancel, and we want grams per mole. So if we want atoms in the denominator to cancel and be left with moles in the denominator, what units do we put in the numerator of that third term?
6.22 times 10 to the
Yep. We put units of atoms in the top. And 6.022 times 10 to the 23rd atoms per 1 mole, so atoms cancel. And unit-wise, we have units of grams per mole, which units of grams per mole is the molar mass. So can I simplify this number-wise? How?
I was just nodding.
Oh. What do you think?
6.022 times 10 over 6.
Yep, those two terms factor out. Yep. So numerically, all we have is 63.55. And the units we have are grams in the numerator and moles in the denominator. So that's just, and you could do this with any element, any average atomic weight or mass to molar mass. Cool. So the decimal serves two purposes. A decimal number on the periodic table for each element is how much it weighs in AMUs, an atom of that type of element, and it's also its molar mass. So let's take a look at what some of that might look like. So here's some elements: zinc, carbon, magnesium, copper, sulfur, silicon, lead, and tin. By the way, tin, SN, that is one of the relationships you're going to have to memorize. So if we looked on a periodic table, these decimal numbers would match up to what the periodic table said, because what the title of the slide says, or what the caption says, is this is representing 1 mole of atoms of each of these types of elements. Cool. This is similarly, we have copper, sulfur, mercury, and helium. And each of these cases, again, it's 1 mole. And it goes back to, like, you know, did I really count these 20,000? No, but I counted enough of them to scale up and to know that I had 20,000. So more thing. Again, with the whole, this is 1 mole of everything. 1 mole of each of these elements: sulfur, magnesium, tin, silicon, and copper. Just to kind of get a visual. So let's work some problems now. It's a really, this sort of problem that we're going to kind of finish up with here is, like the slide says, if you know the molar mass, if you know the grams per mole of anything, you can use that to go back and forth between grams and moles of that thing. Keep in mind that molar masses vary by what substance you're talking about. It's like a physical property of that stuff, is the way I think of it. So what I started to say is this conversion going back and forth between grams to moles and moles to grams, it's a very important basic conversion in chemistry. So we're going to work a few problems. Again, the thing in brackets probably wouldn't be there. So this would read how many moles is 0.487 grams of calcium. Okay. So my first term is going to be that 0.487 grams of calcium over 1. My next term, I want units of grams to cancel. I'll be left with units of moles. I'm going to use the molar mass of calcium. When working these sort of problems, I really encourage you to jot down in the margin before you work the problem. I guess you wouldn't have to, maybe, but on my answer key I do, especially early on. I go to the periodic table, I find the decimal number for calcium. It happens to be 40.08, and I'm after grams per mole. So, but I need to unpack that. G/MOL does not work in working chemistry problems. To unpack that for calcium, it means these two things. There's 40.08 grams of calcium, 1 mole of calcium atoms. In 1 mole of calcium atoms, it would weigh 40.08 grams of calcium. I could also flatten it out and make it an equality. It's like a, it's a physical property, it's a quality for how calcium rolls. So to work this problem, again, my first term is going to be the grams of calcium. And just to kind of, you don't necessarily have to, the grams of calcium over 1. I should have asked you, so if I want grams of calcium to cancel, what units will be the denominator, or the next term you would say grams of calcium. So I call this the flipped version of the molar mass. So if I do this over 1 grams of calcium cancel, I'm left with units of moles of calcium, which is perfect. We're ready to round this. So is there uncertainty in 0.487 grams? Yes. How many sig figs? 3. Very good. Is there uncertainty in 40.08? Yes. How many sig figs? 4. Thanks. All right. So we need to round according to 3 sig figs, and this is what I got. This is one of those examples where we have this placeholder, a leading 0 after the decimal. So that's not significant, but these are. That's how we get 3 sig figs. Perfect. That's it. I'm liking it. Let's do another one. So that was an example of what? Grams to moles conversion. So let's do moles to grams conversion. So what mass is 1.33 moles of boron? What mass is 1.33 moles of boron? So it's going to kind of take a similar pattern. I'm going to go to the periodic table, look up everything, or look up the decimal number for boron, and it's 10.81. So in context of working this problem, we're dealing with molar mass. So we could say there's 10.81 grams of boron for 1 mole of boron. We could say 1 mole of boron weighs 10.81 grams. Boron, we could say 10.81 grams of boron is equal to 1 mole of boron. All about boron. What did one termite say to the other termite? Boron. Sorry. I know, right? Okay. So if this is our first term, what units go in the denominator of the second term? Moles of boron, exactly. So if we're going to put moles of boron in the bottom, it's going to be 1 mole of boron, and then what numbers go on the top? Yep, 10.81. You got it. Moles of boron cancel. We're left with grams of boron. So let's just jump right to how many sig figs should I round this to? I'm seeing fingers pop up. I'm liking it. Yep. 14.4 grams of boron. And I'll kind of give you, so you guys have had chemistry in high school, so I don't know if you remember, but the reason this is important is when it comes to chemical reactions don't happen like 10 grams of this and 5 grams of this. Chemical reactions happen by 2 moles of this and 3 moles of this. So we're going to have to go from grams to moles and moles to grams. All right, so let's take it up a notch. In this one, we're dealing with lead, which is no problem. We have a periodic table. We can look up decimal number for lead, no problem. We're given the mass of lead, and we're supposed to knock out not the moles of lead, but we're supposed to take it all the way. Instead of moles, we want counted number of lead atoms. You can do that. So to kind of diagram this, the only way, sometimes there's more than one way to skin a cat, which really refers to not kitties, but catfish. But I think the only way to do this is to start with the grams we were given, and then we're going to go to moles of lead, using the decimal number for lead, the molar mass for lead. And lead's a weird one. I don't know if I'm not sure why we only have 1 decimal instead of 2 decimals. But on periodic tables, you'll see, that's right here. You see what I'm saying? Like bismuth, oh my gosh, they have 5 decimals here. For thallium, they have 4 decimals here. And I think it has to do with it being unstable, radioactive, and I'm not sure. I should look that up. But anyway, the decimal number for lead is there's 207.2 grams of lead in 1 mole of lead atoms. So that will get us to moles, and then we go all the way from moles to atoms, like we did the first type of problem we worked earlier today. Once we have moles, we know the relationship. 1 mole is approximately equal to 6.022 times 10 to the 23rd, in this case, lead atoms. Cool. Well, here we go. The first term is going to be the mass that we were given. Is there uncertainty in these maths? Okay. I'll see. Yeah, 3 sig figs. Cool. All right. So if we want units of grams of lead to cancel, what units will go in the denominator of the next term? Grams of lead. Yep. So that's our molar mass. That's the flipped version of the molar mass, isn't it? I'll put that first term over 1. And this is the, anytime you see, for me, if anytime you see mm, that's the molar mass. Cool. All right. So grams of lead have canceled. We have units of moles of lead. So if we want units of moles of lead to cancel, what units need to be in the denominator of our next term? Moles of lead. Yep. So in that case, it's going to be 1 mole of lead in the bottom and 6.022 times 10 to the 23rd lead atoms in the top. Perfect. So I bet we're all on the same page, but now remember in situations we have what? 3 terms that are multiplied together. And the way I think of it is kind of the divisor is one big long divisor. My units are perfect. I just need to pull my numbers. So in the top I'm going to have, oops, in the top I'm going to have 0.330, 1, which I wouldn't have to write down, 6.022 times 10 to the 23rd. And in the bottom, the only number I have that's not 1 is 207.2. So those are my numbers. I guess my point is just make sure that you can do this sort of calculation. Some students like to kind of gather it, write the number, take one last division. Parentheses are great, I think. You can open parentheses, da-da-da times, da-da-da, close parentheses, hit your divide by key, and in this case, you just have one number, so you don't use new parentheses. Okay, so fingers, how many sig figs? I'm liking 3 also. Where was that the other day? I cleared it all. Was it this one? 3. Very good. So to show 3 sig figs, of course we show it in the coefficient. I don't know what the unrounded value but 3 sig figs 9.59 times 10 raised to the 20th power. And you might be like, now does that make sense? So what is that? Is that a little more than a mole or a little less than a mole? It's a little less than a mole, yep. And so if you backtrack this mass, well, it's a lot less than a mole. It's a 10 to the 23rd, so a factor 3. So anyway, this mass is that many moles, or that many, excuse me, cute little lead atoms, not moles. Okay, I gotta stop talking so fast. I'm not sure, but slow me down if I start talking too fast. So,
We need to start asking.
What's that?
We need to start asking.
Yeah, or start asking more questions. Okay, so anyway, that's how far I wanted to get today. If that works for you. And we're out early again. One of these days.